Okay, so we'll start the next today, and I'm sure everybody had a nice rest yesterday. After the hard day of lectures, you had the whole evening to yourselves, and I'm sure everybody really is totally rested for another hard day of lectures. So we're starting with again Angus Macintyre, lecture 3 in interactions of logic and number theory. Okay.
Could you turn me on or something?
Turn you on?
Yeah.
This motherfucker works, Angus. Can you help with this?
Can you hear me? Is that okay? Yeah. Right. Okay, so I'm going to begin today with a slight departure from the notes. I want to say something about the ultra-product construction from a rather abstract point of view, designed to be perhaps more palatable to the geometers and number theorists. It is a point of view which has been around a long time, but isn't really easily found reflected in the literature. So, at the end yesterday, I'd raised the issue of uniformly limit. Well, let's try this one. Yeah. Okay. Uniform elimination for the QPs. And I remarked that the elimination that I had given for individual QP didn't really go uniformly because, well, for various reasons, one of them being the definition of the valuation ring in terms of P. That's not actually the most critical thing. There are other factors. If you just look at it closely, you simply don't get a uniform elimination by my methods. You get hints of what might be a uniform elimination. And the essential difficulty is that, in some heuristic sense at least, any such uniform elimination for the QPs would imply some uniform elimination for the residue fields. Now, of course, there's no issue of elimination for an individual residue field. It's a finite structure. It's got a trivial elimination. But if you ask for an elimination uniformly in the FPs, as I suggested last time, you begin to get into rather deeper waters. And it ultimately relates to the issue of, which I think is in any case of independent number theoretic interest, deciding if a sentence in the language of field theory holds in all finite fields. So this relates to what we may call a decision problem for the class of finite fields. So somebody gives you a sentence and asks you to decide once and for all if it's true in all finite fields. A variant question would be perhaps more natural from the standpoint of number theory. Decide if it's true in all but finitely many finite fields, or decide if it's true in all but finitely many prime fields, etc. There are numerous variants. Finite or prime fields. And that would include in particular the issue of deciding whether a system of Diophantine equations is solvable in all finite fields. And that's clearly related to Hilbert's 10th problem. Of course, we know that you have failure of local global in that generality, so it doesn't give you any positive information even if you get a decision procedure here. So Axe, this problem had been certainly posed by the Tarski school, was a well-known problem for many years. it was solved by Axe by means of a model theoretic analysis of limit entities associated to the FPs. Now, these limit entities are so-called ultraproducts of the finite fields, and I want to discuss this ultraproduct thing in greater generality because we'll use it again. I've said in my first lecture that the ultraproduct construction was developed extensively by the Tarski school. It was discovered by Skolem and had also been used by many other people outside of logic. Gelfand told me that he had considered, he claims, even ultraproducts of the finite fields in the 1940s. Lang had considered them in the early 1950s. Okay. Right, this is the point of view I want to take, that we have some language, L, and we have a family MI of structures. And of course, I leave structures completely vague. In this context, there'll be rings or fields or valued fields, things of this kind, valuation rings, etc. Now, what we want to do is to think of this as a family living over the discrete space I. So we have and over the point I, we have MI. Okay. Now, this discrete space has a Stonechek compactification. Which can be identified in different ways. Let me give several of them. I has associated to it a Boolean algebra, namely its power set. So here I have B is the power set of I, a Boolean algebra. And a Boolean algebra is also a Boolean ring, a ring satisfying the identity x squared equals x. So I'll think of this indifferently as a ring or a Boolean algebra. Now, if I look at it as a Boolean algebra, the natural things to consider are ultrafilters on the Boolean algebra. And the Stonechek compactification is made up of these things. I'll describe the topology in a second. On the other hand, if we want to think of it as a Boolean ring, the natural objects are prime ideals, and that's the same as maximal ideals. So equivalently here, prime equivalently maximal ideals. So I really want to think of this, I'm going to think of this space as really a spectral space. But it's technically convenient for model theory to think of it rather on the ultrafilters. Basically, it's a dual point of view. So the idea is that in any case, I topologize this beta I, which is really, in some definite sense, the spec of the Boolean ring. But I'll think of it in terms of ultrafilters. I topologize it by giving basic open sets of the form the ultrafilters. So these are, if I write D as an ultrafilter, to which a given x doesn't belong, let us say. All right? But that's the same as the d's to which the complement does belong. So this space is totally disconnected, it's compact, totally disconnected space. Now these spaces are ubiquitous in logic, and in some sense model theory is really just about these things. Now of course this entity has associated to it a dual, a maximal ideal. It's just obvious. We've got a dual maximal ideal in the ring. Okay. So I'm going to play this game of thinking of beta I indifferently as consisting of ultrafilters or maximal ideals, depending on my mood or what's convenient. One is convenient sometimes, another is convenient on other occasions. Okay. Now, X is a subset, excuse me. Yeah, X is an element of the Boolean algebra. It's a subset of I. Okay, that's kind of, this will get a bit vertiginous after a bit. This epsilon's sort of gone every different way. I warn you about that. But for the moment, X is a subset of I, or an element of the Boolean algebra, so an element of the ring. So you can see when I dualize here, I'm going to get the natural open sets in the spectrum of that ring. Okay. Now, what I'm going to do is I'm now going to create, just out of this data, over an element D in this Stone-Check compactification, an MD. I'm going to do it for every D in the Stone-Check compactification, and I'm going to do it by a sort of sheaf theoretic method. So let's go back to the original discrete situation. Here we have this discrete space, and now we have a basic open set here, okay? And I can take it in either of these forms, okay? Let me take it as, let me take here a basic open set, a basic open given by the D's such that X is in D. Okay, so I'm really using the complementary thing here. Take a basic open set of that form. Okay. Now I want to essentially describe a sheaf here by erecting over this basic open set an entity. Okay, so I attach to this the product for I and X of the MIs. Okay. And I clearly have natural restriction maps if I cut down the set over which I take the product. Well, the basic open set is determined by a subset of the index set, basically. Yeah. So I'm assigning to this basic open set here this thing, which is an L structure. I mean, general nonsense. I can form products of L structures. I mean, if I take fields, of course, I'll end up with rings, not domains, etc. If I started with ordered abelian groups, I would end up with lattice order groups and lots of different things. That doesn't matter. Clearly, I've got some kind of pre-sheaf arrangement here. I've defined it on the basic. Excuse me?
Yeah,
Sorry? Yeah. Now, if you just tinker with it, I've actually defined a sheaf here. I mean, I've given the, I can extend this to the general opens, and I've defined a sheaf here. In fact, this is not on just on this should be beta I, sorry. I should say beta I here now, sorry, beta I. Yeah.
So it is the basic question, but the product of those structures always exist, or
Well, there's a slight problem here. There's a natural definition to give of it. I mean, the L will have both operations and relations, and I define them point-wise on the product. I mean, coordinate-wise on the product. There is a natural, it's going to be, the point to stress is that you may start with interesting entities and end up with something rather uninteresting here, okay? So this doesn't look very promising in terms of getting anything mathematically interesting, but you now go to a D here, and you ask yourself, what is the stalk of this sheaf? Okay, and so there will be something above here, the stalk. Of the sheaf. I mean, this is general nonsense. I mean, anybody can do this. And I think it's clear this point of view was known to Mumford. I mean, there are remarks in the Red Book which suggest that. And many people have told me they knew this for a long time, and many logicians knew this for a long time. Okay, the question is, what is this? I mean, I would derive the existence of a stalk by general kind of categorical nonsense. The question is, what is it? I also have the point that I've embedded I in the Stone-Check compactification. I should have said that. A particular I here goes to the principal ultrafilter. Of elements containing, of sets containing I. Okay, and it corresponds to principal ideals. So it's not too difficult to see that over an I actually have Mi, the original Mi, but I've got these new things. What are they? What properties do they have? Now, they have rather fantastic properties. I mean, there is a sense in which you could base all the first-order model theory on this construction. This is a point of view that I think Cochin flirted with briefly in the around about 1960. And other people like Morley were certainly aware of this point of view too. Okay, I want to tell you something about these structures. And it turns out that these structures, MD, they are like the original structures in the sense that if these are fields, these are fields. If these are algebraically closed fields, these are algebraically closed. However, these might be finite fields, and these might be infinite. So, okay, so I want to explain briefly the fundamental theorem about this construction. Now, how do I represent MD? In most abstract way. The elements of MD, in a sense, they're to be thought of as germs. Germs of sections, basically. In other words, I have around this point D has lots of sets in it. There's lots of products of the MIs attached to it. These are functions. I have a notion of germ associated to that. I mean, again, it's so much general nonsense, I'm not going to spell it out very carefully. So the elements are essentially germs. Say living on some, the sum is varying, some product I in X, Mi, where X is in D. These are functions, and I have a notion of an obvious notion of germs of functions. I start shrinking the index set. Okay, there's a hidden equivalence relation, but I'll write these germs as if they were functions without specifying exactly what their domain is. So I write these as functions. F. Okay. Now the fundamental theorem in this subject of algebra products, and the theorem from which the compactness theorem of logic follows, and most of model theory can be made, or in terms of which most of model theory can be interpreted, is about continuity of satisfaction as you converge towards a point D here. What happens in the corresponding structures? You have in fact, there were moments when I thought this should be the official slogan of the Association for Symbolic Logic, that you have this continuity of satisfaction. What do I mean by that? Suppose I have elements, say I sub alpha, in the index set in I converging to a D. I mean, it's general nonsense again that I is dense in its Stonechek compactification. Okay, so I start converging from the index set to a D. Okay, what does that mean in terms of the topology? It means that if I take any particular set X in D, eventually these all get into X. That's what it means. If X is in D, eventually all I alpha are in X. So this, you have this. There's a lot of epsilons around here with slightly different roles. That's exactly what the topology means. So suppose I've got, I'll do it only for elements of I converging to D. I could do it for elements of the Stonechek compactification converging to others. The same theorem is going to be true. Now I want to say in what sense M of I alpha converges to M of D. So I want to give some sort of meaning to that. It has no a priori meaning. And the meaning is that it converges in satisfaction. I'll explain what that actually means. Fix a formula. And fix elements of MD that I can slot in here. Germs represented by functions. Since they are germs and since I've got convergence, these things are going to be defined nearby. So I'll just assume that they are defined everywhere by throwing away a bit. Okay. Now, the theorem basically is that this is the theorem of Jerzy Wash, a Polish model theorist. It's certainly one of the most beautiful theorems in logic, also with a very simple proof. I mean, I'm dressing it up here, in a sense, that in the limit, MD satisfies phi of F1 to Fn for any formula, if and only if the i's in I, well, say the I alphas, or the, what do I want to say? Well, let me say it slightly slovenly. The i's in I such that Mi satisfies phi of F1 of I, Fn of I, is in the ultrafilter. So now there's an awful lot of epsilons. It's a bit confusing. They're somehow functioning in a sort of dual way. Now, the meaning of that, if you just check it, is the following. And this is proved by an easy induction, with the most difficult case being induction on complexity of phi, the only difficult case being existential quantifier. The meaning is the following. That the truth value is an element of the two-element field, if you like, just to be perverse. There are only two of them, anyway. The truth value of phi F1 I alpha Fn I alpha converges in discrete topology to the truth value in other words, it must stabilize. This is slightly more refined than that statement, but they're probably equivalent. So satisfaction is continuous. Now,
If you want to emphasize that you may as well write F1D through Fn.
yeah, exactly. You're right. Yes, of course you're right. Yeah, that's correct. You've probably just revolutionized logical notation. Yeah. All right. Now, what I want to stress then is the following, that we started with the discrete family, Mi. We've ended up with what we can think of as a continuous family, MD. And I would prefer, because of connections with axes work, to think of these rather as M sub p's, where these are in the spectrum of the Boolean algebra. And I like to think of these as non-standard primes in some sense. Now, because of this theorem about truth value stabilizing, you see that essentially anything true, that if you had something first order true for all of the MIs, it would be true for the MDs as well. Just by this theorem. Because the I is dense in the other thing. So in particular, if we started with fields, and we passed through these rather grotesque rings, But in the limit, again, we got back fields. One can also see that if you started with algebraically closed fields, you get back algebraically closed fields. If you started with real closed fields, you get back real closed fields. If you started with p-adic fields, you get back p-adic fields. And you get back, there are other things like, I mean, this is a very functorial construction. Let me give you just one example, probably enough. If the mi are valued fields, with residue field ki, kd is a value field with residue field, excuse me, md is a value field with residue field kd. This is a tremendously functorial construction. It's functorial basically for everything in first order logic. Excuse me? Same for the value group, yes, of course. I mean, if the value group is a Pressburger group, the same is true for the other thing. And moreover, it is, everything commutes, right? I mean, in fact, what I want mainly to stress is the functoriality of this.
But the theory of any given MD can be larger than the intersection of all the theories.
Oh, yes. I mean, the things can diverge a bit. I'm now going to, I want to apply this to issues of uniformity. So, let me say about this. And I want also to give a, I mean, this will give a precise meaning to what I said at the end last time about the non-standard finite fields, or the infinite finite fields. Yeah, I mean, let me perhaps concentrate on that example while we still have the picture. Then I'll come back to issues of uniformity. Probably the most interesting case for this course is when you take I to be the set of primes, ordinary primes in Z. Okay, and M sub P is, let's say, first of all, FP. But later, I'll also consider instead of FP, I might consider QP, or I might consider FP alg, the algebraic closure of FP. So I could slot any of these into the family. I would have three different families. Now, the question is, what about the, MD in those cases? And I'm only interested in MD for D, which are new, non-principal ideals or ultrafilters. Because for the old I's, I just get back the original structures. That's easily seen. Well, in this will be the first case. Let me say this will be the second. This will be the third case I'll deal with. Okay. So 1, MD is characteristic 0. That follows immediately from continuity of satisfaction. Because you start losing characteristic 2 after a bit, characteristic 3 after a bit, characteristic 4, and the only thing left is characteristic 0. But what is it? This is an example of, these were discovered by Axe, or at least perhaps they were not discovered by Axe. People knew their existence before, but Axe basically discovered all the essential information about them. What properties do these things have? Let me just write it as K. How convenient. The first thing is that we know it's Galois group. And this means, I said yesterday, perhaps a little too quickly, this condition on a field that it has Z hat as its Galois group is elementary. It says the field's got exactly one extension of each dimension. So it's a statement about coefficients of polynomials. And we all know it's true for the finite fields. It's proved there by counting or something. Counting no longer makes sense in the infinite model, but this survives. Okay? This property was sometimes called quasi-finite, I think, by Serre. The crucial property discovered by Axe. So this field is not algebraically closed. It has extensions, after all. The crucial property discovered by Axe is that K is what is called now sometimes PAC, standing for pseudo-algebraically closed. I think it's horrible notation, but we're stuck with it. I think Yershov's notation is better, regularly closed. And let me explain what that means. No, that is the point. I mean, well, I'll have more to say about this later. There's an issue of canonicity. It depends what you would like to say. I mean, you're not going to be able to give any intelligible rule for what the extension of dimension 7 is, because and this is an excellent question, in fact, because it will lead to things I want to discuss later. I mean, you can't say it's, given by adjoining some root of unity, for example. It's not, because as you go to infinity, the behavior over the primes changes. The thing is, our knowledge of the original finite fields largely comes along with and is due to our knowledge of the Frobenius. And the issue will come up in a little while as to what happens to the Frobenius. Well, the Frobenius on FP, of course, is trivial, but the Frobenius on the extensions is not. And the point is, to describe an extension of dimension 7, we basically have to look at x to the p to the 7th minus x and split it. And how that splits depends on the prime. And by the time you get to infinity, it's unintelligible. So there's no axioms that will answer your question. There are no axioms in this language that will answer your question. But it is really the fundamental question about this.
Maybe one more question. Is the ultra product of FP algebraic closure, the algebraic closure?
It's not the algebraic closure, but it is an algebraically closed field. This is an example. This is a very good. The question was, basically, does algebraic closure commute with this D operation? It doesn't. Typically, the ultra product of algebraically closed, the ultra product of the algebraic closures of fields is much bigger than the algebraic closure of the ultra product. That is because, essentially, you can cut across the dimensions. Well, it's perhaps not crystal clear from this point of view. It's crystal clear from the set theoretic definition of ultra products that, in a sense, you create. Well, let me just answer that quickly, make give people some sense of since I want to be talking about algebraically closed fields in a minute anyway. The point is that you know, as I converge, so your picture would be something like this. I have say ki's, and I have them inside their algebraic closure, and I sort of converge in whatever sense to kd, and I converge to ki alg d, and the functoriality certainly gives me a map here, so on. And Walsh's theorem gives that this is algebraically closed. But the point is really, I mean, I can really take the ultra product of this diagram, okay? And then I have here elements of bigger and bigger order over ki. And ultra products of them begin to exist in the limit. And these are not finite dimensional over kd. That's the basic intuition. So let me come back to this thing. Regularly closed about k just means that if say v finite type, etc., I mean just given by polynomials, is an absolutely irreducible variety over k v has a point in k. So I said yesterday, trying to be a little bit picturesque, these fields are essentially algebraically closed, except that they've got finite algebraic extensions. It really means that the Hilbert-Nullstellensatz survives, except for zero-dimensional phenomena. Now, I mean, this was really a turning point in our subject. The first time that one really made contact with very serious number theory. Axe derived this from the quantitative aspects of We's work on curves over finite fields. In other words, it's derivable from the estimate for the number of points on an absolutely irreducible curve over a finite field. I want to stress that this property was an infinite list of properties. It's one for each family of varieties, basically. It's not true for the finite fields. It only becomes true in the limit. I think I say quite a bit about it in the notes. We're a bit short of time. But it depends essentially on the fact that the estimate for the number of points on an absolutely, say, irreducible curve defined over a finite field, the basic estimate, the error term in the estimate, depends essentially only on the genus of the curve. The genus of the curve basically depends only on the degree of the way you present it. It doesn't depend on the coefficients of the curve. And this is the thing that makes the thing get to be true in the limit. It's definitely not true in the individual finite fields. Okay, there is a huge literature on this notion. There is the book of Fried Yarden, largely about things of this kind. This book is, I guess, a centerpiece for one of the projects, so perhaps we'll hear some more about this later. Now, I want to stress that these two things they're not linked. There are many fields which are PAC which don't have this kind of Galois group. However, there is a very severe constraint on the Galois group of a field with this property. And it's ultimately a cohomological one. It goes back to work of Grunberg. If you have this property, if the field has this property, then its Galois group has got to be a projective profinite group, which is a fairly severe constraint. And conversely, a projective profinite group is the Galois group of such a field. And the property of being of the Galois group being projective for a field is first order. That is in this unpublished paper of Cherlin and Van den Ries and myself, and also in Yard and Fried, and in many other places. So let me say two things. I want to get back to the finite field situation. Couple of things about this. People have studied PAC fields in great generality. You might take the point of view that these are monsters. You know, they have been created by means of the ultrafilter construction, which is an axiom of choice thing. And I guess you might feel like Deligne evidently does when he writes in the Hodge theory too about his horror about things like embedding the p-adics into the complex numbers, sort of axiom of choice phenomenon. These are very similar. These you're not going to get at these things very readily without some kind of axiom of choice. You can get at them. You could do what Skolem did to construct special kinds of ultra product. I mean, their existence certainly doesn't depend on the axiom of choice. They also exist in nature, depending on what you mean by nature. Yarden proved, following a suggestion of Axe, that if you look at inside the Galois group of Q, and you take a probabilistic point of view, you start picking an automorphism at random, look at its fixed field, then with probability 1, it satisfies these two axioms. The thing is also very much implicated with Chebatarev's theorem and so on. This is all in Axe's Annals paper. I don't have time to go into it. A more beautiful example than Yarden's was discovered by Popp very much later. And there's a serious misprint in my notes at this point. I forget which page it is. Well, perhaps tomorrow I'll correct my errors. I say that the field, if you take the field K of totally real algebraic numbers, that it is PAC. It's not it that is PAC, it's when you adjoin the square root of -1, it's PAC. Now that's an explicit field of definite interest, which is PAC. Okay, so a great deal of work in model theory of fields has concentrated on this, and it was brought to light by Axe. The other thing I want to stress is that regularly closed, when Anand, in perhaps his first lecture, was describing Robinson completion process that led you to ACFA, it was remarked that similar completion processes would lead you from fields to algebraically closed fields, from ordered fields to real closed fields, etc. If you work in the category of fields and you consider only regular embeddings, so you impose some structure that forces your extensions to be regular, you can do this by certain devices, then these fields occur as the completion for the class of fields which have procyclic Galois group, not necessarily Z-hat, but provided you restrict yourself only to regular embeddings. So these also could have been found by Robinsonian methods, but they were not. Now, this is the sort of tip of the iceberg about axioms here. There's a more general class of pseudo-finite fields. Here we're coming here from the prime fields. We may have used general families of finite fields. Okay? We could in that case get characteristic P fields. We could take this family to be FP, FP squared, FP cubed, etc. We would then get a characteristic P field. It would be perfect, it would have this property, and it would have this property. So there are characteristic P examples of this. And, well, as I say, there's a huge literature on it. For me, these remain the most basic examples. Let us now go to QP. So we put QP above the point P of the space. And we ask, what is Q KD. Okay, what kind of field have we got at the limit? Okay. Well, it's straightforward to see that you have a Henselian field. That its residue field is pseudo-finite. And in fact, this residue field is actually equal to, well, what you get from the FPs at D, right? And this is a characteristic zero field. Moreover, the value group by Walsh's theorem is a Pressburger group. It's not Z anymore, it's much bigger than Z, but it's a Pressburger group. Okay. Now, here now is, I'm going to give now an idea which won Axon Cochin the Cole Prize of the AMS. We already know that we understand these things locally in terms of logic, definability theory, and so on. And the arguments, the things I've written down here don't depend on that. They're just general from Walsh's theorem. Suppose I now replace QP, so as I've got my space, and above P, I've got QP. Now suppose I strike it out and I put instead FPT. And now I look at the stock LD that I get from this sheaf arrangement.
You did that only for one prime?
I mean, above each node, for every prime. So for every prime, I do this replacement, okay? And then I go to any point at all in the stone-check compactification and look at the stock there. Henselian, because these are all Henselian. The residue field is this because by Walsh, residue field commutes with the thing. So it's the same residue field. Right? Value group is Pressburger because it was Pressburger back here. Now, yesterday, I said that in the case when we have a Henselian field with a characteristic zero residue field and Pressburger group, its theory is determined by the theory of the residue field. Now, we don't know the theory of the residue field, but we know that these two things have the same residue field. They literally have the same residue field. So the conclusion is that these are elementarily equivalent. So once we went to the limit, these things satisfy the same sentences. They certainly don't locally, because the fields have different characteristics. Okay? Now, so this was perhaps the first serious application of model theoretic methods to a problem in algebra. Florian mentioned in his lecture yesterday that Lang had proved that these are C2. So therefore, this is C2 for any D. Right? And then a compactness argument, just compactness in the stone-check compactification, tells you the following. This implies that for any instance of the axioms for being C2, the p-adics eventually satisfy them for sufficiently big P. For any instance, by that I mean you have a form of a certain complexity, etc. For any instance C2, QP satisfies it, for P greater than or equal to some P0. Because if it didn't, you could produce a convergent sequence going into some D. You don't know what the D is. So this is a very beautiful idea. One hasn't been able to do much more by this. And as was remarked yesterday, this is the full truth of the matter, because the well-known citizen of the French Republic, Terjanian, gave counterexamples. All right, maybe just a couple of more minutes on this. I wanted to say something about uniformities. And I want to say it in such a way that it may be suggestive to the geometers here. So uniformities in this kind of model theory, there are two at least, two kinds. We may work with a definable family of definable sets. That's got a perfectly clear meaning. You take a definable set in a higher dimension and you specialize some of the variables. Okay? So within and probably of more interest to number theorists, uniformity across P in situations where this makes sense. If we're dealing with fields, we may have properties defined over Z. Okay, so that would make sense in all characteristics. We would ask about the uniformity within certain interesting families, like across the p-adics, or across the finite fields, or even across algebraically closed fields. Okay, so across P, I'll leave that vague as to what that might mean. Now, of course, algebraic geometers are accustomed to subsuming these in one framework, in a scheme theory framework, but we don't in logic. It doesn't quite fit at the moment. So let me just give one, an instance of each for today, and I'll return to this tomorrow. Let's do this one, since we're discussing primes. The most primitive version of this is to consider the Lefschetz principle for algebraically closed fields. I really haven't said anything about characteristic P algebraically closed fields. I said that Tarski had done the situation of C, but he had done much more than that. He had done algebraically closed fields of any given characteristic, showed the theory is complete, etc., etc. Now, simply by compactness, or by the arguments I've given here, of course by other methods as well, you can deduce a Lefschetz principle. I mean, the idea is, in this case, you still work over the same set together with zero. You've got the primes and then zero. And over P, you put some, let me just write it as CP, some algebraically closed field of characteristic. P, if you like, and you can put some algebraically closed field here. Okay? And then you can do all this stone-check compactification and create all sorts of other algebraically closed fields over a D or a P. Okay? They are all algebraically closed by the continuity of satisfaction. And you can ask, what is happening if I, and it's fairly obvious that you can converge into something of characteristic 0 from characteristic P. Just more or less by the same arguments as I gave for the finite fields. By the continuity of satisfaction, the truth values of sentences are not going to change after a certain point. And that's the Lefschetz principle. That if something is true for algebraically closed fields of characteristic 0, it's true for algebraically closed fields of sufficiently high characteristic. There's more to it than that, and I say a bit more in my notes. But basically, the Lefschetz principle fits into this picture. Let me give one other example of, but I want to say much more about the Lefschetz principle in my last lecture. The Lefschetz principle becomes more interesting if we start to address the question of bringing in Frobenius. Because Frobenius doesn't exist in characteristic 0 in any natural way, but this construction gives it a meaning. If I took these algebraically closed fields here carrying their Frobenius, I wouldn't know what to put in at characteristic 0. On the other hand, there is something most of the time in characteristic 0 by Walsh's theorem. There's an automorphism. What kind of automorphism is it? Now that leads on beyond Axe's work, and in fact, it was thinking about this that led to the discovery of ACFA. Turns out ACFA is closely connected to this. The theory of ACFA is really the same as the theory of Frobenius's, or Frobenii, non-standard ones. In other words, maps like x to the power p, where p is a non-standard prime or something. Anyway, let me just give one final thing about families, which can also be expressed easily in this format. Suppose I have let me work, for example, in the reals. And I take a family, let us say, x sub lambda of semi-algebraic sets, a semi-algebraic family of semi-algebraic sets.